So let me introduce you to the topic, but I believe that everybody is almost familiar with the theme. Besides the application of explosive materials in ammunition and armaments, they can have several civil uses, for example, in construction engineering, for mining, and also for metal cladding and welding of metal plate. In the process of explosion welding, the energy of detonation is used to achieve a metallurgical bond between the two different metal materials that practically couldn't be welded on some other conventional method or techniques. So this is a solid state process that produces the high velocity interaction of two dissimilar metal materials by a controlled detonation. And we can differentiate two roles of these plates. The first metal plate is the flyer plate, and the second one is base plate. The cladder material or a flyer plate can be placed parallel or inclined at some certain angle to the base plate. Then explosive material, which is most often in the form of powder or some consistency that can be placed onto the upper plate in even or uniform layer, is distributed over the top cladder material. Then the activation of detonation is done and waves are generated. So due to mechanical bonding between the two metal materials, the joining is taking place. Here on this slide, we can see one a little bit complicated diagram, which is actually showing us some limits of potential welding process. To perform explosion welding, we need to be in between certain limits of velocity of detonation of the applied explosive. Also, we need to respect certain limits regarding the angle of the inclination between the two metal plates, and also to respect some other properties of the materials which are being welded. So here in the middle, where it says wavy interface, it is the best area regarding the parameters to do the explosion welding. Also, explosion welding can be done in the area where it says straight interface, but the connection or bonding is better with the wavy interface between the two metal plates. Several advantages must be mentioned regarding the explosion welding comparing to other methods. First of all, very large plates of metal can be welded together. Very dissimilar materials can be welded. This process takes a very small period of time, and it's not too expensive. Also, one important thing to mention is that we do not have heat affected zone when performing explosion welding. But also there are some drawbacks. For example, the metal materials must have certain impact resistance and ductility, so they shouldn't be brittle. The geometries of the welded parts should be simple, like flat plates or cylindrical parts, conical or tubular. And the cladding plate or the flyer plate shouldn't be too large because of the manipulation and other limitations of the process. Also, this process causes a lot of blast and noise, so this should be controlled if possible. Which are the possible applications of explosion welding? For example, different types of metals, like some base metal material with some thinner, more expensive or exotic metal alloy. Also, we can use this methodology to weld parts for aerospace reinforcing materials. Also to produce heat exchangers, some special tanks, special vessels, special tubes, for some cutting tools, etc. Let's say something about the explosive materials that can be used in this welding process. First of all, we must know that the detonation velocity depends on several factors, like, for example, the type of explosive, the composition of explosive, and the thickness of the explosive layer. We can split the explosives into two groups regarding the explosion welding. The first group are the explosives with a higher velocity of detonation. For example, TNT, oxygen, hexogen, pentrit. or some extruded or plastic explosive compositions like data sheet. And on the other hand, we have middle to low velocity of detonation group, which are actually not some pure explosives, but oxidizers like ammonium nitrate, ammonium perchlorate, amatol, and similar compositions. Also, some weaker explosive materials like nitroguanidine, dynamites, and some penthrite with reduced velocity of detonation. Most often, we need to use a lower velocity of detonation when doing the explosive welded because we wish to avoid the deformation or possible damage on the flyer plate and the welded joint. In our study, we have tried to use explosive Amonex, which is industrial explosive, most often used in mining, which has a lower to middle detonation velocity, to weld two different metal plates. One was the aluminium 2024 and steel 0345. This combination of the two metal materials, when welded explosively, can be used, for example, for connecting some aluminum roofs with some metal steel masts or antennas. This can be used in structural engineering, in civil engineering. So we can also produce aluminum stainless steel pipe for use as cryogenic joints and connection to liquid gas storage containers or vessels, and also in shipbuilding. First, before we have started the experimental procedure of welding process, we have tested the properties of the Amonex explosive. We wanted to experimentally confirm the properties. First, we have measured the bulk density, and the second thing that we have measured was the velocity of detonation. The producer has given some certain characteristics which were declared, for example, like velocity of detonation to be 3,200 meters per second, but we wanted to check this. And what is important to say about this Amonex explosive regarding its composition, that the most of it consists of ammonium nitrate, like an oxidizer, and a small amount of TNT with some very small amount of inert additives. Then we have done the welding procedure. We have taken two metal plates, one from aluminum and the second of steel, of dimensions 15 times 20 centimeters. The thickness of the steel plate was 8 millimeters and the aluminum plate was 3 millimeters. We have placed the standoff distance between them at 4 millimeters and activated Amonex in quantity of 200 grams above the upper plate, which is actually equivalent to 196 grams of TNT. We have used also one wooden frame to keep the Amonex explosive in place because it's a powdery consistency, so it doesn't split over. And after the welding procedure was done, we have performed several tests to inspect the quality of the welded joint. Of non-destructive techniques, we have done the ultrasonic method and infrared imaging. And afterwards, we have cut the samples from the welded plate to do the microscopic analysis on the cross-section of the welded joint. First, let us see the results of the Amonex explosive quality. The bulk density was a little bit lower than it was declared. This is important thing to know because this means that if we apply a certain height of explosive layer on the upper plate, it might not detonate always, or it might give a lower velocity of detonation. But when we have measured the detonation velocity according to our internal standard, we have got the good result. The velocity of detonation was about 500 meters higher than the declared minimum value from the producer. Here on this slide, we may see the results of ultrasonic test of the quality of the welded joint. The black area on the right image presents the area where we have obtained the good welded joint. And out of this area, the metal plates were not welded. So we may notice that basically the middle of the metal pieces was well welded, and on the edges where the standoff dispensers were, and on the part where the red dot is, where the explosive was actually activated, we have a non-welded part of metal plate. Here we will talk a little bit about the ER imaging technique, which was applied to check the quality of the welded joint. We have recorded the metal plates from both sides, from aluminum and steel side, with infrared camera. First, we have immersed the sample in hot water, and afterwards we have tracked actually the cooling process to see if there was some difference over the surface of the plate regarding the registered temperature values. And here on this slide, we may see the steel side of the examined plate. On this steel side, we have one part where the corrosion appeared. So this part has registered values of higher temperature because of this appearance. But also on the edges, we may observe some areas of non-welded joints. On this slide, we have observed the aluminum side of the metal plates, and we may observe one deformation that have occurred on the place where the initiation of the explosive took place. Actually, the aluminum was a little bit more sensitive to this impact of the detonation cap, which initiated the blast of the used Amonex explosive. And on that place, we have this circular deformation, which had reflection and a little bit higher values of temperature. But on the other hand, further, when we have recorded after several more frames and during the time when the cooling of the sample was taking place, we could observe different behavior, just like in an ultrasonic method. Near the edges and near the place where the standoff distancers were placed, we could notice the areas of non-welded material, and not only displaced with the mechanical deformation which I mentioned. And here on this slide, we can see the microscopic analysis of the microstructure of the welded joint zone. What can be noticed on each of these images is the appearance of intermetallic zone. Actually, during the welding process, there happened partial melting of the aluminum, and this is why this intermetallic zone is present. But on all the images, we can observe that the welded joint is well obtained, and it has good quality. But what should be noticed is that we do not have the typical wavy structure which was expected for explosion welding. This is actually the consequence of the quantity of the explosive and the low bulk density. We have tried to weld two more samples on this way, but with lower quantity of explosive, and we couldn't. So this is the first quantity with which we have achieved the welded joint. So probably in the future we should try to increase the quantity or the thickness of the explosive layer over the plate of aluminum. And to conclude, we have successfully applied this industrial explosive Amonex to weld aluminum and steel plates. Two methods, non-destructive methods, ultrasonic testing and ER method, have confirmed this. Metallographic test has shown us that we do have a good weld joint, but it can be even better with some improved parameters of welding. And in our future research, we will base on different quantities of explosive, but also we will try to do the welding of larger metal plates. So that's it. If you have any questions, I will be glad to try to answer.